Hi everybody, welcome back. In this video we're going to be looking at how to use Laplace transforms in order to solve a second order differential equation. So here's the example that we've got. You'll see we have second order differential equation where your dependent variable is y and your independent variable is t. We also have a set of initial conditions that we're going to be using in solving this differential equation. Okay, so you'll see here our independent variable, as I said, is t, which means that your equation is at the moment in your time domain. So we're going to be applying the Laplace transform to the entire equation in order to put it into the frequency domain or the S domain, which means that your variable is going to be with S in it. So let's do this. So I'm going to take my differential equation and say 2 t squared y dt squared 5 dy dt minus 3y equals 6. And then I apply the Laplace transform to both sides of the equation, right? And that is the same as writing it as the Laplace transform of each of the terms in the equation. So it is 2 transform of your second derivative 5 times the transform of your first derivative minus 3 times the transform of y, and then the transform of 6, right? Now, the Laplace transform of your second derivative is just a formula, right? There is a derivation for the formula which you can go through. So if you look on your table, and you see here, I've got a table, and right at the bottom we've got that. So this is the second derivative, right? And this is where your function f of t is. If you move from this column to that column, you will get your Laplace transform. So the transform of this second derivative is going to be this equation here, or this formula here, should I say. Okay, so we can write this as 2 times s squared f of s minus s f at 0 minus f dash at 0, right? So this piece, this whole piece here, is the transform of your second derivative, right? So I'm just going to push this up here and go on to the next line so that we have some space. And that's going to be 5 times the Laplace transform of your first derivative, which again, if you look at your table, is going to be all the way down here. The Laplace transform of the first derivative is going to give you this formula here, right? So it is going to be times s f at s minus f at 0, right? So this here is that one over there, right? And then, oh, that mustn't be plus, that must be minus 3, and this is just the Laplace transform, so it is going to be f of s, and that is equal to the transform of 6, which is a constant. And if you look at your formula, where your value is a constant, it's going to be the first one on your table. So it's going to be 6 over s, right? And now we're going to simplify that and neaten it up a bit. Okay, so these expressions here, those are initial conditions, right? So this is where t is 0, your function is going to be 0, and here is where t is 0, your derivative in this case is going to be 0. It's not always the case, but for this problem it's going to be. All right, so let me just write this out so it looks a bit neater. I'm going to get rid of the brackets and everything. So I've got 2s squared f of s, 2s f at 0, 2f dash at 0, plus 5s f at s, minus 5f at 0, minus 3f at s, and all of that is equal to 6 over s. Okay, so then our initial condition says that where f, your function at 0 is going to be 0. See, because here your function is y. So that over there is 0. Your first derivative at 0, where t is 0, is also 0. So that goes to 0. This one also goes to 0. So what we end up with is we've got 2s squared f of s. We've got 5s f of s. And we've got minus 3 f at s equals 6 over s. Right? So all of that simplifies to this equation here. And what you'll see on your right hand side, you see that you've got your terms, each of these terms has an f of s in, right? And the f of s is your Laplace transform. So we're going to make that the subject of the formula. So we've got f of s, 2s squared, 5s minus 3 equals 6 over s. Okay? Then we can say f of s is equal to 6 over s, 2s squared, 5s minus 3. Okay, so now we've got an expression for f of s. And what we want to get, right? Remember, when you're solving the differential equation, what do you want to get at the end? You want to get f of t, okay? Or you could call it also y of t, right? Because in this case, your dependent, not independent, your dependent variable is y, right, over there, right? Or should I say over here? You can see. Okay, so this is what you want to get at the end. So if you know what f of s is, you can then use your inverse Laplace transforms in order to get f of t, right? Or in this case, y of t. Okay, so let me just write out. I'll write out this f of s. So we've got f of s equals 6 over s, 2s squared, 5s minus 3, right? So from here, you want to apply the inverse Laplace transform in order to get your function in terms of t. So this is in the frequency domain because it's in terms of s's. You want to now take it back into the time domain. So our strategy then is to start with the denominator. And you look for anything on your table that has the same form as this denominator, but you won't have, right? Because if you multiply this out, you've got a trinomial. So there's nothing like this on there. So then you try and see, can you factorize? Can you simplify this bracket even further? And you can. You can say 6 over s, and this is going to simplify to, it is 2s minus 1, s plus 3, right? Let me just check. Gives you that gives you minus s plus 6s, which will give you plus 5s. Okay, so now you've got factors in your denominator, which means you can use partial fractions in order to simplify, because that is just going to be equal to a over s, b over 2s minus 1, c over s plus 3. Right? And you'll see that the denominator in each of these terms, the forms are the same as ones on your formula sheet. Okay, so let us find what A, B, and C are. So we have 6 over S, 2S minus 1, S plus 3, A over S, B over 2S minus 1, C over S plus 3, right? So if I was to put all of this over the same denominator, I'm going to have 6 over S, 2S minus 1, S plus 3, and that's going to be A times 2S minus 1, S plus 3, B, S times S plus 3, and that's going to be CS. I'm just going to squeeze this in here, over 2S minus 1. Right, and this is also going to be over S, 2S minus 1, S plus 3, right? Now, because you've got the same denominator and you're working with an equation, it means that the numerators have to be equal to one another, right? So we would then have that 6 is equal to A, 2S minus 1, S plus 3, BS, S plus 3, CS, 2S minus 1. Right, and now we can find the values of A, B, and C. And I'm going to say, in order to find that, I'm going to let S equal to 0, right? And then I'm going to get 6. That is going to be 2, or this is going to be 0, so that's going to be minus 1. That S is 0, so that will be 3. That S there is going to be 0, which means the entire term is going to go to 0. That will also be 0, so that entire term will also go to 0. So these two are just going to fall away because they become 0. Okay? That means that A is going to be, that's minus 3, so it's going to be minus 2. Okay? Then, in order to find B, I'm going to say let S equal a half. Right? So let S equal a half. So we've got 6. If you substitute a half in here, this is going to make that 2 times a half, which means it's 1. 1 minus 1 makes it 0. So if this is 0, the entire term becomes 0. Then here it will be B times a half plus 3. Here, if I put in a half, you're going to get 2 times a half, which makes it 1. 1 minus 1 is 0. Okay? So we end up with just these terms here. This is going to be B is equal to 2 times 2 is 4. So this is going to be 7B over 4. And that means that B is going to be 24 over 7. Okay? So let's have a look and see what C is going to be. And in order to find C, I'm going to substitute in minus 3. I'm going to say let S equal minus 3, which means that I've got 6 is going to be equal to minus 3 in here. It means the first term is going to add up to 0. Minus 3 in your second term, you're going to get minus 3 plus 3. So the second term is going to add up to 0. So then I'm just left with the third term. And it's going to be 2 times minus 3 minus 1. Right? Let me just move that up like that. Okay? So we've got 6 equals to minus 3C times, that's going to be minus 6 minus 1, so it's minus 7. So 6 21c, which means c is going to be 6 over 21, which is the same as 2 over 7. Okay, so now we have values for a, we have a value for b, and we have a value for c, right? Which means we can now say that f of s, we can substitute back into this expression here, right? You see there? So f of s is going to be, let's just rewrite this so that it's easier to see. I'm just going to rewrite him like this. A over s, we had simplified our equation, s minus 1, c over s plus 3. And we found a was minus 2, I think, yes. Minus 2 over s. B we worked out. B is 24 over 7 times 1 over 2s minus 1. And C is 2 over 7 right? Now, if you look at the denominators of each of these terms, you'll see that there's the same form as something on the table, which takes your function from the S domain into the time domain. So we're looking for the inverse Laplace transform here. Okay, so if I look at the first term is in the exactly same form as number 1 on my table, because that's just, the denominator is just a s, right? If I look at my second term, it is the same form as number 7 on the table, but what you'll notice here is that in front of that s in the denominator you need a 1, right? You can't have a 2 like that, so I'm going to have to factorize out the 2. So before I take my inverse, I want to get everything in exactly the same form as on the table. You cannot find the inverse of parts of the equation. So you can't have a mixture of variables in your answer. When you find your inverse, you need to do it for the entire equation, right? So for every single term in the expression here. So I'm going to say 24 over 7 times 2, because I'm factorizing out that 2. Right, that's what I'm doing. This one is okay, so we can leave that one as is. We're going to leave that one as is. Okay, so then I'm going to get f of s equals minus 2 over s, 24 over 14, plus 2 over 7 times 1 over s plus 3. Okay, so now every single term in the denominator here, for each of these terms, you have something on your table that is in the same form, right? So we can then say we're going from S domain into time domain, right? So it's going to be f of t. The first one is the first one on your table. So here you've got k over s. Let me just lift this up a bit, maybe you can see better. The first one, right? Which means that in your time domain, that's just going to be minus 2, okay? 24, you can simplify that fraction. If you look at the denominator here, that would be the same as number 7 on our table here, right? So that is just going to be e to the half t. The third term is going to be also number 7, right? But in this case, b is going to be minus 3. So that's going to be e to the minus 3t. Right? So then you can say, instead of f of t, you can just say that that's y minus 2 plus, that's going to be, what's it, 12 over 7 e to the half t, 2 over 7 e to the minus 3t. And that is the solution to your differential equation using Laplace transforms. I hope that video was helpful. Please stick around for another one.